This is a short lesson on problem-solving techniques for force-related physics problems. Here are the steps that we're going to follow for solving force-related physics problems. It's a good idea to develop a standard system of solving these problems. That way, when you encounter an unfamiliar problem, even if you're not exactly sure what to do, you have a place to begin and you have steps that you'll follow, and hopefully they will lead you to a good solution in the end. So here's what I recommend to organize your solution. First, read the problem and focus on understanding the scenario and which objects are the objects of interest in the problem. Don't focus too much on exactly what you need to do to solve it yet. Just make sure you understand the setup. Second, find the forces acting on the object. Third, draw a free body diagram for the objects of interest. 4. Create a table of known and wanted quantities and break every vector into x and y components. 5. Reread the problem. Focus on what it asks you to find and on clues about the net force. 6. Carefully write out Newton's second law. And finally, 7. Identify the equations which can be solved to find your solution and solve the problem. Let's try out this problem-solving method by looking at an example problem. A skier who weighs 650 newtons is traveling at a constant 10 meters per second down a ski slope angled at 20 degrees below horizontal. What is the force of kinetic friction acting on her skis? The first two steps of this method are to read the problem and focus on understanding the scenario and which objects are the objects of interest in the problem, and then to find the forces acting on the object. Well, I've already drawn a little sketch of how I visualize the scenario. Here is the skier. The slope is 20 degrees. In the problem, it describes the 20 degrees as being below the horizontal, but that's a complementary angle to the one that I've drawn in this problem, and so we can also think of it as being 20 degrees above the horizontal, measured at the bottom instead of measured at the top. So I think I have a pretty good idea of what's going on here. One technique for finding the forces acting on the object, I really like it, is to draw a circle around the object of interest. In this case, it's got to be the skier. There's really nothing else happening in the problem. Now, forces are going to happen whenever the object is in contact with something else. And so the major contact point is here on the snow at the bottom of the skier's skis. And so I have to think about what forces are acting, and it could be more than one. It's important to realize it could be forces. So one thing that I know is acting is a normal force. So I write that as a capital F with a N on it. Normal force points perpendicularly to the slope, and so it's at kind of an angle from the horizontal in this problem. I also believe that there is kinetic friction acting. This should be kind of small in a realistic scenario, but I'm not sure how realistic this one is. I also know that anytime a problem takes place on Earth, I should definitely consider weight. I know that the weight of the skier points towards the center of Earth, and so that's straight down in our picture. The problem says nothing about drag or air resistance, and it's standard procedure in introductory physics to ignore it unless told that it's relevant. The problem didn't mention it, and so I'm going to go ahead and ignore it. The next step is to draw a free body diagram for the object or objects of interest. I've gone ahead and preloaded a XY coordinate system here. It's important to know what your coordinate system is and to be absolutely consistent. And so I would recommend always, always, always adding an XY coordinate system to your free body diagram. So to begin with a free body diagram, we need a dot that represents the object of interest. And every object of interest will have its own free body diagram. A free body diagram describes only the forces acting on one object. So the object in this case is the skier. And in our sketch before, we already had a bunch of these drawn in. So there's a normal force that points straight along the positive y-axis, and I'm going to name that Fn, normal force. There's a force of kinetic friction, which points uphill, so that's going to point along the negative x-axis. And then there's weight, which points straight down, so that's not going to be aligned with my axis. Weight there. So something else that I would like to go ahead and add to a free body diagram, if I know anything about it, is the net force. So there's a step coming up that says I should reread the problem, but if I can put this in a free body diagram, I always want to. I read the problem and I remember that it talked about a constant velocity. If the skier is moving in the same direction down the hill at a constant speed, then that's an object in motion staying in motion, so there's no net force. And so the net force, if I write that as the sum of forces, has to be 0 in this case. And I'm going to go ahead and write that as a reminder. In some problems it's interesting to know the velocity, and so you might just want to make a note to yourself that that arrow represents the velocity. I could write in a number if I wanted, 10 meters per second. Now that's a very complete free body diagram. In many cases it would be sufficient just to draw the dot that represents the object, the skier in this case, and then the arrows that represent the forces. But it helps you enormously to have this coordinate system set up, to know something about the net force, and to make a reminder about any motion that's happening. We're working on step 4 of this solution method. It says create a table of known and wanted quantities and break every vector into x and y components. So I've set up a table. This one is really just for forces. And so every single force which is acting in the problem should be in this table. Every single force should also be in your free body diagram, and so that's a great reference for setting up this table. Alright, so the first force that comes to my mind is the normal force. So I'm going to go ahead and write an F, normal. I want to write down its components. According to the XY coordinate system, which I set up, normal force does not act in the x direction, and it acts in just the y direction, and so I'll write it over here. Another force that comes to mind is the friction, which was kinetic friction. The kinetic friction acts entirely in the x direction, and it points in the negative x direction, so there's 0 in the y. Finally, there's weight. Now the way I drew it, weight did not line up with the axes of my coordinate system, which means that the weight has both x and y components. So to figure out those components, I need to draw a triangle. I don't want to really clutter up my screen here, but I think it's important to remind you of what this looks like. So here's the weight. It points straight down. There's a component that points along the slope, and there's a component that points into the slope. The angle, the 20-degree angle, is at the bottom of this triangle that I've drawn. So I know that that's a little small and untidy, but I just wanted to remind you where these things come from. So the x component of weight in the coordinate system I set up is a positive number, and it's actually positive mg times the sine of the 20 degrees. Sine because it's the opposite of the angle. Meanwhile, the component along y is a negative pointing component. It points into the ramp, and so this is going to have a negative mg, and this one is a cosine of 20 degrees, and that's because the y, the part aligned with the y-axis points into the ramp. Alright, I'm not quite done. I would like to add these up, but strictly I'm going to add up the x's and keep those separate from adding up the y's. So in x, I know that the sum of the forces in x is equal to mg sine of 20 degrees minus the friction force, and in y, I know that the sum of the forces is the normal force minus mg cosine of the 20 degrees. All right, so step 5 suggests that we reread the problem, focusing on what it asks us to find, and look for clues about net force. Step 6 says to carefully write out Newton's second law. All right, as I mentioned before, I already picked up on the clue that this skier has a constant velocity, which means there is no net force. This gives me the information I need to be able to carefully write out Newton's second law. So based on my table before, I knew that the sum of forces in the x direction was going to be equal to mass times the gravitational constant times sine of 20 degrees. This is the component of the weight minus the kinetic friction force. And I know that the sum of forces here is equal to 0, that there is no net force. So mg sine of 20 degrees minus the force of friction, that's equal to 0, which makes them equal to each other. And really, at this point, I realize I've solved the problem, because the problem was asking, remember step 5 says, check what it's asking. It was asking what this force was. Well, the force is mg sine of 20 degrees. Do I know what mg are? I do. That was given in the problem too. That was 650 newtons. All right, so I can go ahead and put that number in here. 650 newtons times the sine of 20 degrees is equal to the force of friction. All right, we arrived at step 7 almost before we knew it. In step 6, we were writing out Newton's second law carefully and realized that we had the solution, that the force of friction was equal to the skier's weight times the sine of 20 degrees, which was the angle of the hill. So once we realized that, the only thing that was left to be done was to carry out the mathematics, which I've gone ahead and done, and it's written on the screen here. And my result to two significant figures was 220 newtons. I'll go ahead and put a box around that. So that's the way that the solution method should work ideally. If you've taken the time to be careful about identifying the forces, if you've written out your table, put everything in the components, and you begin to write out Newton's second law, then you should see and recognize the equation which is going to get you the solution that you want. So we have completed this example problem using the method listed. As a final look, we'll just go back and take a look at the steps one last time, but that pretty much concludes our lesson. Just to review, here are the recommended steps for organizing a solution to a force-related physics problem. First, of course, read the problem, but focus on understanding the scenario and picking out which objects are the objects of interest in the problem. Second, you want to find the forces acting on the object or objects of interest. Third, draw a free body diagram for the object of interest. If there's more than one, then you will need more than one free body diagram. Fourth, use that free body diagram as a reference and create a table of all the known quantities and wanted quantities. Break every vector into x and y components. Even if you don't know what numbers to put in for something, write it out in formula form. Give it its mathematical definition. Fifth, reread the problem. This time, focus on what you're being asked to find and focus on clues about the net force. Sixth, use what you know about the net force to write out Newton's second law carefully. You'll have a distinct Newton's second law for each axis of your coordinate system. Finally, as you've written out Newton's second law, it should become apparent which equations you're going to use to actually put in numbers and solve the problem.